thick green packet about functions and graphs. We're not going to give you one big test on the whole thing. It's not going to happen. We cover 1.1 and 1.3. I think we skip 1.2. And then we take a test. Oh my gosh. 2 sections and we take a test. 1.1 is 3 days. It's going to take us at least 3 days to get through all the objectives in section 1.1. And 1.2 is another long one, you know. So there's a definite break after that from what we're talking about with functions and graphs to new things that we're going to learn. So it just is a natural place to do that. So here, we have a lovely picture of some ceiling trusses. And it says one of the central principles of economics is that the value of money is not constant. It's a function of time. Since fortunes are made and lost by people attempting to predict the future of money, or what's going to go on with the value, much attention is paid to quantitative measures like the Consumer Price Index, which is a basic measure of inflation in various sectors of the economy. And it goes on to talk about where we're going to see this. But we have experienced tremendous periods of inflation in the United States. Not you guys, but I mean as a country. And that would be usually around wars. That's what happens. You know, your money becomes precious because the country is generating products for the war, you know, making ammunition and those types of things. So it's harder to get a hold of all the goods that you need for your everyday life. But our inflation has been nothing compared to some countries. Our value for our money has generally stayed within reason. There are some countries in Africa where their country goes to war. The day before the war, they go in, they buy their products with their normal amount of money. They get a gallon of milk for $4, whatever it is. And the next day, they literally have to bring in a wheelbarrow of their currency to purchase that. And that's because their economy has collapsed because of their war. And we have never seen that, and we're very fortunate. But we have a lot of things that keep us from having those things happen. For instance, we have the Federal Reserve Bank in the United States. And so they take care of a lot of inflationary problems as we go through different periods in our history. So our overview of Chapter 1 is going to be talking about those types of things. The Consumer Price Index is supposed to let us know, are we getting the same bang for our buck from day to day? You know, if a gallon of milk, which is one of the guidelines they use, if a gallon of milk starts to raise in price too much, well, then something has to be done about that, because if inflation gets too high, your average everyday consumer won't be able to afford them. And so they make changes so we can all get what we need. So our overview of Chapter 1, numerical, graphical, and algebraic modeling and the problem-solving process. A lot of what we're going to do today is just going to be on that board. That's about as far as we'll get. Functions and their properties, we'll have to talk about that tomorrow. The 12 basic functions, and that's as we get further on into this chapter. Combinations and compositions of functions, so using a couple of functions together at one time. Inverses, which would be reversing the x and the y and solving for y. Graphical transformations of our functions, moving it right, left, up, down, all that good stuff. Creating functions from formulas, graphs, verbal descriptions, and data. Well, in a nutshell, that's kind of the standard. You know, we want to be able to do all of that as we go through Chapter 1. But it's not going to happen overnight. It is not. We've got a lot of little pieces to put together. So our modeling and equation solving today, we're going to be able to set up models to represent real-world phenomena, numerically, algebraically, and graphically. Absolutely. We're going to do that today. Combine algebraic, graphical, and numerical methods to solve and verify solutions. A little bit of that, you know, kind of putting a couple of things together at once and talking about them with numbers, of course, and the data. Use the problem-solving process to model and solve real-world applications. So that's really what all of this is, you know, trying to make this connection to what's going on in the world. And understand some of the limitations of the graphical method. Graphing is great. Been around, depending on what research you look at, 40 BC. You know, they've been graphic for a long time. That was before they had algebra. So graphing's been around. But it does have limitations. It's not the most accurate way to find things. It's just not. But it's a pretty good method. You know, it is math, so it's a pretty good method. So like it says, we're going to understand the limitations of just graphing things all the time. We certainly would rather have an algebraic model, especially if we're going to make predictions about the future. So mathematical model is a mathematical structure. It could be a graph, an equation, or a table. Lots of various things that we use when we're trying to figure out, well, we're trying to make predictions. We want to know, what can we expect in the future? And often the best insight can be gained by using a variety of models to analyze a situation. One of the newest jobs out there, which is actually right now starting to pay quite a bit, is going to be data analysis. I know you guys are on the internet a lot, and surveys, they always pop up all the time. You know, you purchased this from us. Will you take this short survey? So there's somebody at Target, at Kohl's, at wherever, that takes all of that information and says, okay, what does this tell us as a corporation? And those jobs, they're going to need tons of people to evaluate that information. I was just talking to somebody this morning whose daughter is going to be working at a research marketing facility, and she's doing just that. If a product doesn't sell, it's going to be her job to bring in a focus group, which is just, you know, random people out there, to come in and tell them, what don't you like about this product? You know, what can you change about it that would get you to purchase it? And then make those changes. So those jobs are there, and we always are looking for new technology jobs with good math people. So numerical models, ones in which numbers or data are analyzed. Numbers or data are analyzed. That makes it a numerical model. So down here, this says we're going to track the minimum wage. And the numbers in table 1.1 show the growth of the minimum hourly wage. And it says this is from 1955 to 2005. Yep, we can see that right over here. The table also shows the MHW adjusted to the purchasing power. So this is what they made, which, by the way, look at that, 75 cents an hour in 1955. And over here, what could they purchase in 1996 with that money? So that's part of using that consumer price index to say, okay, here's what a person could have bought with this money way back then, and what could they buy now? Have a good day. All right. So this, we would all look at 75 cents and say, how on earth did anybody make it back then? 75 cents an hour? Think about that. You work 8 hours. You're not making a lot of money there. But as my father-in-law likes to tell the story, back in those days, his mortgage was $113 a month. They didn't know how they were going to make it, how they were going to pay that $113 a month. But now, most mortgages are around $1,000 or more every month. So obviously we've experienced inflation since that time, but the minimum hourly wage is supposed to rise with it to make it so that Americans can do things like buy a home, buy a vehicle. So answer the following questions only using that data. A says, in what 5-year period did the actual minimum hourly wage increase the most? I don't know, we got a lot of numbers there. And I noticed it said 5-year period. Well, that's what these are. So what we really have to do is figure out how much is this going up each time. So let's just do this all together here. From 75 cents to $1, how much is that going up? A quarter, 25 cents. From $1 to $1.25? 25 cents again. $1.25 to $1.60. 35 cents. $1.60 to $2.10. 50 cents. Ooh, $2.10 to $3.10. That one, that's about $3.10 to $3.35. Back to a quarter. $3.35 to $3.80. 45. $3.80 to $4.25. Another 45. $4.25 to $5.15. 90 cents. $5.15 to $5.15. Goose egg. Didn't get an increase in that time period. So in which 5-year period did the actual minimum hourly wage increase the most? What was our biggest number over there? Yeah, $1 from 75 to 80. We didn't have to do any fancy math for that. We just had to look and see, well, what is the change for every 5 years? But then it says for B, in what year did a worker earning the minimum hourly wage enjoy the greatest purchasing power? Well, that's different. Greatest purchasing power, where do you see that? 1970. 1970. By the way, that was right before a recession. And that's what we usually see. Those are indicators of a recession. If people are able to buy too much, what do? They go into debt. And if we have too much debt, then we get a recession. So there are indicators. There's never a sure bet of when a recession is going to take place, but there are indicators. And like I said, the Federal Reserve was built to watch those indicators for us and let us know, hey, things are getting out of hand. Raise the interest rates so people stop spending so much money. C, a worker on minimum wage in 1980 was earning nearly twice as much as a worker on minimum wage in 1970. Let's see. 70, they were making $1.60, and 1980, $3.10. Well, yeah, $1.60 times 2 would be $3.20. And it says, yet there was great pressure to raise the minimum wage. How come? Yeah, the purchasing power was definitely dropping. So that's the reason there was so much pressure. The purchasing power was dropping. Now, why does that matter? If you don't have money, you can't spend it. And if you don't spend it, our economy goes in the toilet. You know, we're supposed to earn money so we can spend money and buy goods in the United States. So it was that purchasing power that was the problem. And then we go right from purchasing power to prison populations. Table 1.2 shows the growth in the number of prisoners incarcerated in state and federal prisons at year's end for selected years between 1980 and 2005. So right over here. Is the proportion of female prisoners increasing over the years? So here's what we don't want to do. We don't want to go over here and say, well, yeah, look at that. They're getting more female prisoners. They're saying proportion, which means we probably better be looking at percentages, because normally that's the way we look at simple data would be, okay, what percentage of the total population are we talking about? Because if more people are getting incarcerated, well, maybe this isn't an increase. Just overall, maybe everybody is going to jail more. It's just how it works. So what we want to do is we want to get into our calculators and we want to put some data in. Let's see. We better clear your memories first, because if you have something loony in there, you're going to go halfway through this and you're going to tell me you've got a problem. So second memory, which would be second plus number 7, 1, and 2 on the 8/4. Okay? Everybody get a memory cleared, RAM, yeah, all that good stuff? Okay. So what we want to do is we want to put statistics in, data in. So we have to go into stats, and that button is just here to the left of the left arrow. Hopefully some of this will come back to you. And then number 1, we want to edit. And yes, I cheated because this thing is so slow. So what we're going to do is we're going to put in the data, and then we're going to stop where it says list 4. So this says use years since 1980. So instead of 1980, this will be our 0 year. 5, 10, 15, 20, 25, and 30. So we'll put that into list 1. Everybody got the 0, 5, 10, 15, 20, 25, 30? Something's wrong? It'll be okay. You'll just be off by 1. Sometimes that happens when there's a glitch in the ship itself. It's like doing whatever it should have grabbed this one. List 2, just female. List 2, just the female. Oh, we didn't need the 30. Did I go too far? I did. Yeah. We don't need the 30. Take the 30 off. Thanks, Tommy. I thought I was writing too big and I was off by one. But that makes sense. At 2005, we should be stopped at 25. We're going to get the 30 out of there. All right. Now, list 3 is going to be the total. That's these. Except for Dylan, who's off by one. And I want to show you a really cool feature. The graphic calculator. To calculate percentages, you always find what you want and divide it by the total. But that will give you a decimal. So like 0.03, you'll have to figure out that that's 3%. Well, not that that would be a horrible thing for us to do, but we really want the calculator to figure out females divided by the total, what percentage of the population are they? So what we're going to do is we're going to go to list 4, and we're going to tell list 4 to do that math for us, so that we don't have to. Really nice feature. Does everybody have those lists in? Okay, so we'll go to the calculator, and we're going to tell it list 4, stat, and then again, I know you guys were already there, but just in case anybody doesn't have this. Now, I'm going to clear this out, and we're going to do the math. If you go all the way up to the top of the name of the list, you can tell the calculator what you want it to fill that with. So what I want it to fill it with is I want it to take 100, over there. And I want it to take that times the females divided by the total. Well, in mine, that's list 2 divided by list 3. So I'm looking around, where do I get these list names? Well, they're all in blue by the number buttons. So all we have to do is hit second, and then list 2, number 2, divided by second, list 3, parentheses. And when we punch enter, the calculator is going to do that math for us and give us the percentages. Fill them in for us. Didn't have to do anything. So now, the question was, is the female population increasing with the total? Yeah, I mean, pretty obviously, every single year there's been an increase in the amount of females that are in present. So we have to be specific about that. We always want to give what data did we see. I mean, that's what we were supposed to do, was analyze the data. So first thing is we say a big yes. I mean, yeah, we saw that. There's an increase in the females that are going to prison. So what were those increases? Well, it went from approximately 4%, 4.0% to 4.6% to 5.7% to 6.0% to 6.7% to 7.1% as a percentage of the total population. somebody in first hour said, well, why can't we just write, yes, it went from about 4% to 7.1%. Because that doesn't give the whole story. The whole story is there's been an increase every single year. It's not like all of a sudden there was some huge drug bust in the United States and boom, a whole new group of people, females, ended up in prison. Every single year that percentage is increasing. So we want to give as much information as we can about the data in numerical form when we're answering our questions. So now, we went ahead and used our graphing calculator kind of as a spreadsheet, which you guys may have never heard of before. Spreadsheets were before we had graphing calculators. You could get a spreadsheet to do a little math for you. So algebraic models use formulas to relate variable quantities being studied. One benefit of an algebraic model is that it can be used to find unknown quantities by relating them to known ones. So, we use those formulas because we know the formulas to figure out how do we want to compare these things. So example 6, pizza. This is a good topic. Better topic right before lunch. A pizzeria sells a rectangular 18-inch by 24-inch pizza for the same price as its large round pizza, which has a 24-inch diameter. If both pizzas are of the same thickness, which option gives the most pizza per the money? So they're saying, don't think 3D. I don't know anybody that really does when you buy pizza unless you really like deep dish pizza. What they're saying is, what you care about is the toppings. You pay for that stuff that goes on the top. So 18 inches by 24 inches is going to be that rectangular pizza. And then the round one has a 24-inch diameter. So if we just care about the toppings, we really care, bless you, about 2 dimensions here. We don't care about thickness. So 2 dimensions would be the area. How do you find the area of a rectangle? Length times width, base times height. So we need to take 18 times 24, and that'll give us the square inches of pizza. Everybody? All right, 32 square inches of pizza. How do you find the area of a circle? Pi r squared. Area equals pi. Did they give us the radius? No, then we can find it real quick, right? What's the radius if the diameter is 24? It's 12 divided by 2. All right, so pi times 143 plus 452, 389 square inches. So, if all you care about is getting more pizza for your money, which pizza should you buy? The circle. The circle. A round pizza, it has more square inches of toppings. What kind of a dopey mathematical problem? Because you don't just go because you get more pizza. You go because you like the taste. So how many Little Caesars lovers do we have in here? Like Little Caesars pizza. Okay. How about the other cheapie? Domino's. Domino's favorites. Okay. My husband's kind of a pizza connoisseur, so we've had them all over time. Really good one in Now Then, Mama DeLuca's. Anybody, have you gone somewhere that you're like, this is a phenomenal pizza? Where was it? Tell us. Where was it?
It was this place in Wisconsin. It's like this really rustic place, and they flame oven pizzas and
Oh, like the one downtown here, where you can see the fire
like
inside
Pompeii.
the roasted pizza. Anybody else? Phenomenal pizza somewhere? In Chicago? Chicago, yeah. Pizza, Chicago, yeah. No, my husband swears it's Pizza Flame in Coon Rapids. That's the best pizza ever, Pizza Flame. I was there once, and it's not bad, but you know, the pizza. We can't eat Domino's or Little Caesars at our house because my husband cares too much about his pizza. Alrighty, let's start talking about buying stuff. Shopping. Shopping's important. Without it, our economy would make it. A department store is having a sale in which everything is discounted 25% off the marked price. Well, that's not too bad. The discount is taken at the sales counter, and then a state sales tax of 6.5% and a local sales tax of 0.5% are added on. So what's the total tax? 7%. Yeah, it's kind of hidden and split between these two. You know, some people will notice if they go to Dairy Queen and Elk River and you get a medium cone, you pay a different price than if you go to Rogers and you buy a cone. And that's because the county sales tax levels are different. Hennepin County sales tax is always higher than everybody else's because they pay for all of the stadiums down in the cities and all that kind of stuff. So, you know, just how are you going to spend your money? One says the discount price D is related to the marked price M. So you go to the rack of the clothes and you see the marked price. And it says the little formula we can use for that is D equals K times M, where K is a constant. What is K? K is what we care about, which is what are we paying? So if we're not paying 25% because that's the discount, how much is left for us to pay? 75%. So our K constant with this is going to be 0.75, which is of course our 75% as a decimal. So we'll be able to do some math with it. You know, it's great that it's 25% off, but what we really care about is what are we going to pay when we get done? So number 2 says the actual sales price, which is S, is related to that discount price D by this little formula right here. S equals D plus TD. What on earth is this? Sale price equals discounted price plus taxes times the discounted price. And it says the constant is related to the total sales tax, so we need to know what the total sales tax is, and we talked about that. 7%. But in a math formula, what would we use for T? 0.07. Using the answers from step 1 and 2, you can find a constant P that relates S directly to M by the little formula P. S equals PM. What is P? That is just awful, you know, the way they have that worded. Here's what they're saying. Go back and actually do this and simplify it. Actually find S equals D plus T times D and simplify it so that this is really easy to use. So the sale price will be the discounted price. Well, that's going to be 75% of whatever it was marked. I mean, that's why we found that 0.75. We wanted to know how much we were going to pay. Plus 7% of that same discounted price. So there's a little math we can do here. You know, first off, we need to take that 0.07 times 0.75. S equals 0.75 M plus, and 0.0525. Yeah. Well, now they're both M's. They're like terms. So we should just add those together. 0.8025 M. So the question was, what's P? And P stands basically for the percent that we're supposed to pay. Well, as a decimal, it's right there. P equals 0.8025. So it's supposed to be 25% off. But because we have to pay taxes, we're really going to pay how much? Read that off as a percent. 80.25%. Because there's taxes, whatever it is. And some states even tax clothing. So run into that in different states. Now this one says, now that we have this fine little formula, S equals 0.8025 M, we're going to head to the store because everybody brings a calculator with them when they go shopping. Even if it's just a dollar store calculator, take a little calculator with you. You want to make sure that they're giving you the right price. If you only have 30 bucks, ooh, better be a good sale. Can you afford to buy a shirt that's marked $36.99? I don't know, better find out. So, S equals 0.8025. The marked price of this shirt is $36.99. Well, if we want to know if we can afford it, we're going to find out what the sale price is. And they will always round up. We're going to round this normal and say $29.68. You have 30 bucks. You going to be okay? Yep. It'll be the one thing you can buy. You probably aren't going to have anything else in the store that you can purchase for 50 cents. Always going to happen. Well, you decide. You've got a check coming in the mail for $100. So you head to the store with a credit card. You have a credit card. Determined to spend no more than $100 bucks. What is the maximum total value of your marked purchases before you present them at the sales counter? So you're wandering around and you're trying to get an idea of, can I pick one more thing out? Can I not pick one more thing out? Well, we would want to know, what is our limit for those marked prices? That's what we're really looking for. So this is just a little division, and then you'll know. So we have to round down on this one or we won't have that one, but it rounds down anyway. So $124.61. 6 or 7 years ago now, Albertville Outlet Mall, Black Friday, which by the way, businesses are saying, they rumor this every year, but they're saying now there is not going to be a Black Friday anymore. Why would they not want Black Friday? They do. They end up losing money on a lot of things. And they're saying, we give you Cyber Monday anyway. So it's usually a threat. They've done this the last 3 years. So we're not going to give you as great a deals on Black Friday. But anyway, Albertville Outlet Mall, the Izod store there, had a big sale. It said 70% off everything in the store. Well, who wouldn't go in 70% off the store? And if you're there between 9 a.m. and noon, you get the early bird special of another 20% off. So people are walking around the store. 70 plus 20, that's 90% off. I was so proud of the little gal that was working because when she would hear people say that, she'd say, it's still a really good deal, but it is not 90% off. We take 70% off of your original purchase and get a new price, and then we take 20% off of that price. So it's still a really good deal, but it's not 90% off. And you wouldn't believe how many people are wandering out that store. Well, that's what they hope is going to happen, that they'll get you with the math. But we know if you do a little bit deeper looking into it, you're not going to get that good of a deal. Still a very good deal, but not that good. So, what next? Well, we got to do more calculator stuff. I told you we were going to need those calculators today. And what's the time here? The ability to generate numbers from formulas makes an algebraic model far more useful as a predictor of behavior than a numerical model. Indeed, one optimistic goal of scientists and mathematicians when modeling phenomena is to fit an algebraic model to numerical data, and then, even more optimistically, to analyze why it works. Again, there's a lot of new jobs in that. Not all models can be used to make accurate predictions. For example, nobody has ever devised a successful formula for predicting the ups and downs of the stock market as a function of time, although that does not stop investors from trying. Many people have tried to figure out how do we figure out what the stock market is going to do. But mathematically, because there are so many variables involved, it doesn't mean that one day we won't be able to do that, but right now it's just not possible. So if numerical data do behave reasonably enough to suggest that an algebraic model might be found, it is often helpful to take a look at a picture first, see what the data look like. And that brings us to our graphical models. So a graphical model is a visual representation of a numerical or algebraic model. This type of model can give insight into the relationship between variable quantities. So you've gone out and you've collected all kinds of data and you want to know, can I come up with a formula for this to make predictions about the future? Because that's what all companies want. They want to be able to predict what's going to happen. So this says we're going to visualize Galileo's gravity experiments. And Galilei spent a good deal of time rolling balls down inclined planes, carefully recording the distance they traveled as a function of elapsed time. Balls down ramps. He was looking for gravity. His experiments are commonly repeated in physics classes today, so it's easy to reproduce a typical table of Galilean data. So we're going to put this in, but we're not putting it in over the top of that other stuff, because we're going to need the other data. So we're going to put this in as, let's see, we'll need list 5 and list 6. So go back into your calculator. Get those numbers in. That data's in your packet. Hopefully it's not so tiny. It's a bit small. That's not bad. You can see that. So again, it's stats, edit.
Good morning, students and staff. This is just a reminder that after this hour, you should report directly to your ELP time session. ELP time is an evidence-based practice that will help those of you who need additional support with a skill or lesson by offering you purposeful and focused sessions. The additional support should increase your ability to achieve and learn. ELP time is for you. The choices you make and the work you do will make a difference. Have an awesome day. Thank you.
That sometimes clears anything that's moving. All right, you got a bit? Because what we want to do is we want to see this time. And if we want to see it, we have to do stat plots, because this isn't normal graphing, this is stats plots. So that's up here, but it's in the blue. So you have to hit second stat plot. And then you're going to have to turn one on. So hit number 1. And then while Blinky is blinking over the top of on, press enter. So we've got a stat plot on. Now, we are going to have to change the lists, because we put this in the list 5 and list 6. So you're going to have to hit second, number 5, enter. Second, number 6, enter. And then we have to change the limit because our values were not negative 10 yet. So let's see. We had elapsed time from 0 to 8, so maybe negative 2 to 10 would be good for your x's. And then we had 0 to 48, so maybe negative 2 to 50 for the y's. We want to see it. You know, what does this look like? Got it set? Okay, graph. There it is. Now, that does not look like a line to me. That doesn't look linear. But does everybody see how this would be really good as a parabola? So, I like to take that data out of your calculator if you can help it, because I think I'm running out of time here. You probably won't be able to do this whole assignment. I knew we weren't going to get the whole thing done. But maybe just get a little start on some of them where you're just looking at the table and figuring out the changes and all that kind of stuff. So I'll leave a note. We've got the data punched in, but we still need to take a look at that